This looks like ordinary ice. But there is something very different about it. It never melts into a puddle of water. At atmospheric pressure, dry ice changes directly from a solid into carbon dioxide gas at approximately -78.5 degrees Celsius. And producing this extremely cold material on an industrial scale requires far more than a freezer. Inside a modern dry ice plant, carbon dioxide is recovered, purified, compressed, liquefied, and then suddenly expanded to create solid snow. That snow is compressed into the blocks and pellets used around the world. So how does a factory manufacture something this cold? Dry ice is simply the solid form of carbon dioxide, or CO. Unlike ordinary water ice, it does not normally pass through a liquid stage when exposed to atmospheric pressure. Instead, it sublimates directly from solid carbon dioxide into gas. This makes dry ice useful wherever powerful cooling is needed without leaving liquid water behind. Factories can produce it in different shapes, including blocks, pellets, and other compacted forms. But before any of these products can be made, the factory needs a reliable source of purified carbon dioxide. The raw material for dry ice begins as carbon dioxide gas. Industrial carbon dioxide can be recovered from several sources, including fermentation, hydrogen and ammonia production, and other industrial processes that generate concentrated CO streams. The factory does not simply collect ordinary air and freeze it. Instead, it works with a concentrated carbon dioxide stream and separates unwanted substances from it. Once recovered, the CO begins a carefully controlled journey through purification, compression, and liquefaction. The solid block we started with began as an invisible gas. Once a suitable CO stream is available, it enters the recovery system. At this point, the gas is still under controlled industrial flow conditions. Sensors continuously monitor pressure, temperature, and flow rate. Automated valves regulate how much gas enters each stage of the process. This control is important because downstream purification and compression equipment work best when the feed remains stable. The invisible gas is now entering a very visible chain of machines. Recovered carbon dioxide is not automatically clean enough for the next stage. Moisture and trace contaminants must be controlled because they can interfere with cold equipment and affect the final product specification. Depending on the source and application, industrial systems can use scrubbers, filters, adsorption equipment, and other purification stages. Water is particularly important because it must be reduced before the carbon dioxide reaches the coldest parts of the process. The goal is simple: keep the useful CO while removing substances that do not belong in the final product. Before liquefaction, the carbon dioxide must be dried even further. Excess moisture can become a serious problem in cold sections of the system because water can freeze and interfere with equipment. Industrial CO plants therefore use dedicated drying equipment to reduce moisture to very low levels. Depending on the process and application, very low dew points can be required. Additional filtration may then remove remaining trace contaminants before the CO enters the liquefaction system. At this point, the invisible gas is ready for its next transformation. Now the process reaches another major transformation. The purified carbon dioxide is cooled and pressurized under carefully controlled conditions until it can exist as a liquid. Industrial liquefaction systems use refrigeration, heat exchangers, and pressure control to achieve this phase change. The exact temperature and pressure depend on the system design. Once liquefied, the carbon dioxide becomes a compact feedstock that can be stored and delivered to the dry ice production line. The next pressure change will turn that liquid into something completely different. Once liquefied, the carbon dioxide can be held in insulated storage vessels. These tanks provide a buffer between the upstream CO recovery system and the dry ice production line. Pressure, temperature, and liquid level are continuously monitored. The storage system must keep the CO within its intended operating conditions while providing a stable supply to the production equipment. Now the factory has everything it needs: purified carbon dioxide, liquid carbon dioxide, and a machine ready to turn it into solid CO. This is the moment when liquid carbon dioxide becomes dry ice. Liquid CO enters an expansion system where its pressure drops rapidly. At atmospheric pressure, carbon dioxide cannot remain liquid. The sudden pressure reduction causes part of the material to become gas, while the rapid cooling creates solid carbon dioxide in the form of extremely cold snow. That snow is approximately -78.5 degrees Celsius. In many industrial processes, only part of the incoming liquid becomes solid. The remaining CO becomes gas and may be recovered for reuse, depending on the system design. The loose snow now becomes the raw material for the final product. The result is not yet a finished dry ice pellet or block. It is loose carbon dioxide snow. This material is extremely cold and continuously wants to return to the gas phase. That is why it is collected directly inside the production equipment and compacted without unnecessary delay. The snow may look soft and fragile, but the next machine is about to transform it into a dense commercial product. Now the loose CO snow is compressed. A hydraulic piston applies strong mechanical pressure, forcing the snow through a forming die and creating a dense continuous shape that can separate into individual pellets. Different forming systems can produce different pellet sizes for different industrial applications. Blocks are produced using a similar principle, but the snow is compacted inside a mold rather than continuously extruded. And this is the essential transformation. Carbon dioxide gas is recovered. It is purified and liquefied. The liquid is expanded into solid snow. And mechanical pressure turns that snow into the dry ice people recognize. The product is finally taking its finished form. Automation controls much of the process, but the human element has not disappeared. An experienced operator watches the production line for small changes that a sensor may not fully explain. Are the pellets forming consistently? Is the press cycling normally? Is the product breaking apart too easily? Is frost appearing where it should not? These observations require training and process experience. Operators also verify instrument readings, inspect equipment, respond to alarms, and decide when a production adjustment or maintenance intervention is necessary. In a process operating with extreme cold and pressurized carbon dioxide, recognizing an abnormal condition early is part of keeping the entire system under control. Before dry ice leaves the production line, it has to meet the requirements of its intended application. Quality checks can include product weight, dimensions, physical condition, and consistency. A production technician may sample pellets from the line and compare their size and appearance with the specified product range. For blocks, dimensions and mass are important because they influence both handling and sublimation behavior. The product must also remain free from unwanted contamination. Quality control is not about making the dry ice colder. It is about making every batch predictable. Not every piece leaves the machine in perfect condition. Pellets can break during forming or handling, while blocks can develop cracks or fall outside the required dimensions. Instead of automatically treating every imperfect piece as useless, production systems can separate material according to the product specification and process design. Where practical, suitable dry ice material can be returned to the forming process or handled as sublimating CO. The exact recovery route depends on the equipment and the intended product grade. The important principle is simple. Production quality is controlled through separation, inspection, and process correction. There is no ordinary waste stream of melting water here. Dry ice eventually becomes carbon dioxide gas again. That makes ventilation one of the most important engineering controls in a dry ice facility. Carbon dioxide is colorless and can accumulate in poorly ventilated areas, so industrial workplaces use ventilation, gas detection, and operating procedures appropriate to the risk. Storage and handling areas are designed to prevent dangerous concentrations from building up. The same physical property that makes dry ice useful, its ability to become gas without leaving liquid behind, also means the gas must be managed carefully. In a well-designed facility, sublimation is not treated as a surprise. It is built into the process from the beginning. Packaging dry ice is different from packaging ordinary frozen products. The container must provide thermal insulation while allowing carbon dioxide gas to escape. A completely airtight container would allow pressure to build as the dry ice sublimates. For this reason, dry ice packaging systems are designed around controlled gas release and appropriate insulation. Workers or automated filling equipment transfer the required quantity into the container, minimize unnecessary exposure time, and close the package according to its intended shipping method. Every minute matters because the product is continuously disappearing into the air. Dry ice does not behave like an ordinary warehouse product. Even inside an insulated container, it continuously sublimates. That means inventory planning is critical. Instead of keeping large quantities on shelves for long periods, production and distribution are coordinated around customer orders and delivery schedules. A warehouse may therefore function more like a short-term staging center than a conventional long-term storage facility. Containers are identified, weighed where required, assigned to orders, and moved toward dispatch as quickly as practical. Dry ice does not behave like an ordinary warehouse product. Even inside an insulated container, it continuously sublimates. That means inventory planning is critical. Instead of keeping large quantities on shelves for long periods, production and distribution are coordinated around customer orders and delivery schedules. A warehouse may therefore function more like a short-term staging center than a conventional long-term storage facility. Containers are identified, weighed where required, assigned to orders, and moved toward dispatch as quickly as practical. From here, the product enters a race against time. Dry ice is used for temperature-sensitive transport, specialized cooling, food applications, laboratory work, and other industrial purposes. Because sublimation never stops, transportation is planned around the expected journey time and the quantity of dry ice required. Larger shipments can move by road in appropriately ventilated vehicles, while smaller shipments may travel through specialized parcel and air cargo logistics subject to carrier and regulatory requirements. The objective is not simply to deliver a box. It is to deliver enough solid coal that the required cooling capacity remains available when the shipment arrives. The cost of dry ice is not determined by the cold alone. One of the biggest factors is the availability and cost of suitable carbon dioxide. If the coal is recovered as a byproduct from another industrial process, the economics can differ substantially from a facility that must source and transport purified coal from elsewhere. Energy is another major factor. Compression, purification, refrigeration, and liquefaction all require industrial equipment and power. Labor, maintenance, packaging, and transportation add further costs. And then there is sublimation. Every kilogram that disappears before reaching the customer represents material that has already been produced but can no longer be sold in its original form. At scale, efficient production therefore means controlling the entire chain. The future of dry ice production is not simply about making colder material. It is about recovering more carbon dioxide, reducing losses, improving automation, and making every stage more measurable. Advanced plants can increasingly use sensors to monitor pressure, temperature, vibration, product flow, and equipment performance. Predictive maintenance can help identify developing mechanical problems before they interrupt production. Automated handling can also reduce unnecessary human exposure to extremely cold material and high-pressure process equipment. And as industries search for ways to reduce waste, recovering coal that would otherwise be released can become an important part of the overall process design. Asterisk here are 8 facts that make dry ice unusual. Asterisk. First asterisk dry ice is solid carbon dioxide. Asterisk second asterisk at atmospheric pressure, it sublimates at approximately asterisk 78.5 degrees C star. Asterisk third asterisk it does not leave a puddle of liquid water behind. Asterisk fourth asterisk the white cloud around dry ice is largely condensed water vapor from the surrounding air, not visible coal itself. Asterisk fifth asterisk dry ice is denser than ordinary water ice, with density depending on how it is produced and compacted. Asterisk sixth asterisk increasing surface area generally increases sublimation rate, which is one reason small pellets disappear faster than large blocks under comparable conditions. Asterisk seventh asterisk industrial dry ice can be manufactured in several forms, including a piece of dry ice may look simple. But behind that cold white solid is an entire chain of engineering. Carbon dioxide begins as an industrial gas stream. It is recovered, purified, dried, and compressed. Then it is cooled and liquefied before entering the dry ice production system. A controlled pressure drop transforms part of that liquid into solid snow. Hydraulic force compresses the snow into pellets, blocks, or other shapes. Operators inspect the process. Quality control teams check the product. Ventilation systems manage the returning co-gas. Packaging protects the product while allowing sublimation to occur safely. And finally, the dry ice begins its journey to the customer, already disappearing back into the atmosphere one molecule at a time. From captured gas to a solid at -78.5 degrees Celsius, the process is a remarkable example of industrial engineering built around a simple physical principle. Asterisk if you enjoyed seeing how this hidden manufacturing process works, subscribe for more factory documentaries, and tell us which product we should take inside next. Asterisk.